variation in the strain due to the application, that it may be force, it may be pressure, whatever may be the application. So resistivity of the semiconductor strain gauge material is given by, now in the previous case R is equal to rho L by A, here for semiconductor strain gauge it has been given as rho is equal to 1 divided by Q N mu. What is this Q? Q is the change in electron, whatever I have specified previously. Semiconductor, it is semiconductor. N is number of charge carriers that depends on the doping. Mu is the mobility of the charge carrier. Mobility means movement of the charge. What is the problem associated with the semiconductor strain gauge? As I have already specified, that it is going to impact whatever the electrons we are having, or the charge carriers, or the mobility of the electrons, or the motion of the electrons. Now when it comes across the variation in the temperature of the surrounding environment, at that particular moment the mobility, that is exchange of the electrons, or the variation in the electrons for the charge carrier, will increase. That is the property of the semiconductor, and this is going to impact on the performance. This is going to impact on the performance, because the output on which we people are depend are totally based upon the variation in the resistor. Now when we are applying a force on the strain gauge, suppose this is the strain gauge, this is the base material. On this particular base material, if suppose we are having a strain gauge, and no doubt the output which we people are going to get by applying some force on this strain gauge, it is going to be elongated. So we are saying that the strain, this much is the force. Force is directly proportional to the output that is generated over here. Output variation in the resistance generated when it is connected across the Wheatstone bridge. So output is in terms of voltage. Suppose I have considered E0. But at the same time, for the semiconductor strain gauge, if my environmental condition, the temperature of the environmental condition changes, then and then also the resultant output which is supposed to be generated, that is voltage, because resistance is going to change depending upon the variation in the environmental temperature condition. This is the disadvantage. That's why we are using the dummy strain gauge, which will try to compensate the variation in the temperature. That will try to compensate the variation in the temperature. So this is the limitation of semiconductor strain gauge. Now, the problem associated with the semiconductor strain gauge can be resolved by a dummy strain gauge by utilizing the sense of temperature compensation to get the same gauge factor lambda value for a different semiconductor strain gauges. But it is difficult due to the doping. The doping adhesive material that I have specified in the first slide. Arsenide, that material, due to the doping effect, that is PN type of material. Okay. So in other strain gauges, it may be possible to get a small value of lambda, for example, wire. Now the impurity, actually semiconductor, it concerns with the impurity concentration, and in this semiconductor strain gauge, your impurity concentration is between 10 raised to 16 to 10 raised to 20 atoms per centimeter cube. So the resistivity of P-type silicon with a concentration of 10 raised to 20 atoms per centimeter cube is 500 micron ohm meter. It is 500 micron, 500 micron ohm meter is much higher than a copper. It is much higher than a copper. The maximum change will be there in above specified range. If it varies beyond this limit, then there is not much change in the strain. What does it mean? Though the maximum change in the range takes place, then and then also there will not be a much change in the resultant output of the strain. As strain gauge material shows the change in resistivity, and it's totally depend upon the piezoresistive effect, that is change in the length may cause change in the resistance. So the mobility of the charge carrier changes due to applied strain, causing a large change in the resistivity. Applied strain means you are applying some force or some application, pressure or a torque that will cause a large change in the resistivity. So one of the important difference between a conductor and semiconductor strain gauge is a semiconductor strain gauge are essentially non-linear devices. Linear and non-linear. Linear means suppose I am having a graph and from center it is varying linearly. This is a linear one. But however, if I am having a graph and if it varies non-linearly or likewise, this is a non-linear one. So what is the property of the semiconductor strain gauge? It is non-linear with a typically quadratic transfer function. So dr by r is given as S1 epsilon plus S1 epsilon square. What is S1 is the sensitivity, product of sensitivity and strain, plus sensitivity, product of sensitivity and its strain square. So it is nothing but the summation of the two products, summation of the two products, and its operation is a positive temperature coefficient and a negative temperature coefficient. What is positive temperature coefficient? That suppose I am having a wire, and for this wire, if I have applied a force, if I have applied a force, it's no doubt that you people are well aware its resistance R is going to change. So at first instant, if I apply force, its resistance will increase. Its resistance will increase due to change in length. So what is going to happen? Suppose I am having x and y axis. If I have applied force, my output is going to change linearly. My output is going to change linearly. What it indicates? The force that has been applied, force that has been applied with change in resistance, it is going to increase linearly with change in length. Now I have considered the another mean, and in this another mean, if I have applied a force at that time, if I try to plot the graph, this is going to not change with respect to linearly, non-linear output I am getting. Non-linear means here increase in length will decrease the resistance after applying a force. Decrease. That is non-linear output you people are getting. That is NTC, negative temperature coefficient. Negative temperature coefficient. So with respect to temperature, if I want to specify, if my resistance is going to increase when temperature is increased, when temperature is increased, that is positive temperature coefficient. And if my resistance is going to decrease, resistance is going to decrease with increase in temperature, with increase in, that is negative temperature coefficient. That is negative temperature coefficient. So NTC is negative temperature coefficient, PTC is positive temperature coefficient. This is the graph of positive temperature coefficient, and this is the graph of negative temperature coefficient. Okay, so this is associated actually with temperature, variation in the temperature. And why we people are studying temperature? The reason is that the semiconductor is sensitive to the temperature. That's why whether what type of semiconductor material we have used, whether we have used positive temperature coefficient or negative temperature coefficient material. Because when temperature is going for compensation, we have to take this point under consideration. You have to take this particular point under consideration, that when your temperature is going to change, whether resistance is going to increase or decrease. And in proportion to that, you are supposed to design that compensation circuit. So advantages of the strain gauges: high gauge factor, useful. In the previous lecture also we have specified for the measurement of the strain mu, and small gauge length, very small strain gauge sensor. What are the limitations? High temperature sensitivity, then non-linearity, mounting difficulty, mounting on the substrate, performance deteriorate in presence of moisture, means moisture is also going to impact on that one. These are the merits and demerits of the strain gauge. Now, what is